Good morning, everyone. Sorry for the delay. The breakfast was too good. So I'm going to talk about qubits today and their interactions. And I am a theorist, so for me, a qubit is a two-level quantum system, right? So not any two-level quantum. The question is, can it be any two-level system? And the answer is, in principle, yes. And basically, the talk is going to be about molecular qubits. Okay, so by now it should be clear. And you know, as long as it can do something quantum, I'm going to go coherent oscillations, radio oscillations, for example, it can do. I mean, it will do. But in practice, there is 5 criteria which are well understood in quantum information community. They're called DiVincenzo criteria, and they're actually from the paper that this DiVincenzo he wrote on silicon, like quantum dot-based qubits, some like maybe 25 years ago. And they're very reasonable. You should be able to, or you better be able to initialize the qubits in state 0, 0, 0. Oftentimes in quantum algorithm, 0, 0, 0, 0 is your initial state that you're starting from. Then you apply entangling gates. That's one, right? If you cannot initialize your qubits, you pretty much can forget. You're not doing quantum computing, right? At this gate-based quantum computing, I should say, because there's different paradigms of quantum computing, and some of them you don't have to. In some of them, you don't have to worry about. Goes forward, but don't back out. In some of those paradigms, you don't have to worry about initialization, but for gate-based quantum computing is the most popular right now paradigm. So in this paradigm, you have discrete operations like quantum logic gates that you have to do between either one or pairs of qubits, sometimes 3 qubits at a time, but rarely. So this is very important. And now you have to be able to quantum involve. So ideally, you have more coherence time. And what is the problem here is because there's no isolated quantum system, right? So all quantum systems interact with the environment, and coherence is an off-diagonal movement of the density matrix, right? Remember your quantum class, there's a density matrix for 2 qubits, or 1 qubit, even 2-level system. So the density matrix will look like something like, I don't know if we can quickly illustrate that, how noise kills the qubit. This matrix looks like something like this, you know. For a 2-level system, it's a function of time. Actually, diagonal elements are time independent, but the all diagonal elements have some sort of initial value times, exponential of the energy gap between the two, right? So what happens is, like, if you subject it to noise, this diagonal elements don't care. At least if they, let's assume there's no relaxation, and this guy doesn't change with time. So the noise just affects the, let's say, the between the energy levels. Typically, a lot of the time, noise is just, if you measure the omega each of them involved. The frequency of the qubit will be recalculated. We don't say there is a fluctuating magnetic field. And if it fluctuates, it's exponential. You get plus and minus, right? With these fluctuations. If above the wavelength, they all add up to 0. So after we wait some time, which is called typically, T2 time. So your destination before you know it, something like this. So T is greater than T2. Of course, in the equation, so your diagonal elements becomes gradually suppressed. We look at your diagonal elements of the faster than this. Very generic. There's a lot of models, of course, we're not going to go into theory of the systems here. But depending on your noise model and how things go, so this here. So eventually, after you wait many periods, then you time. Your density matrix, let's say T will be in steady state, right? In oftentimes very like this. Right? And this is completely rubbish. This is rubbish. You can do complete quantum computing. right? Because there's no coherence, there's no time dynamic there. It's a the interaction with the environment has destroyed qubit and turned it into computing dysfunction. So it's useful to be able to maintain quantum coherence for a certain time, where, and ideally those oscillations have to be like prominent enough that you can do. So this is essentially underlying quantum gates and all of this quantum information science, right? So if you cannot maintain coherence, sorry, no gate-based quantum computing. Then, of course, the ability to measure or read out qubits is very important, as well as the existence of a universal set of quantum gates, which Kanquan already mentioned yesterday in her talk. This nice dipolar spin exchange quantum gate, which also I'm going to develop a little bit today. So in molecules, we don't have to worry about that too much because there's so many levels and there are gates. So to be had. But in some other systems, it hasn't been so straightforward, like in NMR, for example. Oh, it's lost. It was over. Maybe. Okay.
Sorry, Timur.
Yes.
There's might be a typo on the diagonal. It's supposed to be T2 over T, right?
T over T2. T greater than T2 becomes small. It's like a graph model, like a graph. Usually it's like something more dramatic. If you want to more exact, so it's the decay of the solution, right? So if T greater than T2, it becomes suppressed. Right? You can see it like this. So the envelope decay to 1 over E time, the output this sign became over here. And the terminology is from NMR, where there's a skin plane organization that, oops, now it's a new information here. And I think this is the projector. That's not me, maybe. Oh, it went away. Perfect. Great. Scalability is another thing. So obviously, it wouldn't be useful. I mean, if you had just one qubit, right, you can play with it all day long, right? But it's not going to give you any computational advantage compared to you need many to eventually beat classical computer solution, which is of course a race currently, and Google is involved, and other companies are involved in quantum advance. So Google has, even 3 years ago, they had 53 qubits. So it's really important to be able to, but scalability also probably not so much of an issue anymore because there's Avogadro number of molecules. So in principle, we can, people trap in optical lattices and, hundreds, thousands of molecules. So it's not them. So maybe these two things are not, so read out, anyway, so I'm not going to, of course, address, there's no time to address all of these important concepts, but suffice it to say for now also that seems like daunting, and it is. So satisfying this DiVincenzo criteria for system is very, very hard. And that's why we can have so many competing computing platforms. But for some of the applications like quantum metrology, for example, which I'm going to go into today, you don't need all of these guys. So you can, for example, you don't necessarily need, individual site addressing with some of the quantum metrology protocols, right? Or you sometimes don't need, you definitely need universal setup. You don't need universal setup quantum gates for that. So maybe scalability and that the first, second, and perhaps fifth are very important and universally important. Now, there's also another paradigm, such as, for example, one-way quantum computing and others that also some of this can be relaxed. The question for molecules is, of course, which state we can encode qubits in, right? So, and the molecules have zillions of states, right? And so far, the most popular choice has been the two lowest rotational states, n equal to 0 and 1 with the same nuclear slash electron spin projection. So you just ignore nuclear spins. You say, I have a rigid order and equal 0 and 1. 0, 0 and 1, 0 rotational states are my qubit states. Now, other important and popular choice is the same rotational state and different nuclear spin projection in the ground state. I'll also talk about that a little bit. These are the most important and explored choices so far. But this is a research lecture, so I'm going to dwell a little bit about our work of exploring crazy combinations of qubits. And there's no shortage. You can, for example, pick two different rotational laws, for instance, with different interesting projections. What happened? Hasn't been done. Well, until recently. Then you can pick non-adjacent rotational states like 0 and 2. And finally, other combinations can be had, and also vibrational electronic states, molecules that sometimes we forget about them, but they do exist. And there's research on that. I'm not going to dwell on it. Like most of my talk today will be rotational / nuclear state, which is the most relevant for alkali molecules. Although vibrational qubits research has been going on, I think it's been 20 years since it's been proposed, and it's also very interesting. So let's begin with encoding into conventional rotational states. Great choice. An original paper by Dave DeMille on quantum computing with structural molecules was actually based on this choice. So the choice was to choose 0,0 rotational state as a spin down, 1 level, and 1,0 as spin up level. And this has been overwhelmingly successful. People think about that and talk about that, and they publish lots of papers on that. But these are some of the first papers by Dave DeMille and actually Robin Cotte and Suzanne Lin and Kate Kirby at ITAMP. They followed up with this nice work 4 years after Dave DeMille's paper, which also helped to kind of solidify the foundations of quantum-based quantum. So some of my favorite papers are those two, but of course, forgive me if I omitted some of the important papers. So the beauty of this is that these rotational states, as we heard from John, can be made to interact using long-range anisotropic and tunable electric dipole interaction, right? So this is a great chapter that I recommend for derivations, and I'm going to go in a little bit into derivations today. It's by Michael Wall and Caleb Hazard and Anna-Maria Ray. It's something like 2015 in a book, and the key point is to how do these qubits interact with dipole interactions, right? And the key idea is that you begin with this EDM matrix elements in the qubit basis, which actually, again, John derived already. Yes.
Chapter from a book.
This is a chapter from a book, which I don't remember, but I have a reference to it in our paper, which I'm going to cite. So you can just Google quantum. But also Anna-Maria, I think she has it on her website. Yeah. I think I downloaded it there, but you can get the entire book. There's actually other interesting things in that book. But this is, I think, by far the most interesting at the moment for this lecture. Yeah, this is actually a very nice chapter, and I recommend it to everyone who wants to study not only quantum computing but also quantum condensed matter physics and quantum magnetism. This is master from everything. Okay, so the idea is just to begin with EDM matrix elements in qubit basis, then project out the electric dipole interaction. What does it mean, project out? I'm going to explain it in a second, and then. Of course, we have optical lattice / tweezer setup with pinned molecules. So this is kind of an approximation. There is a lot of things which are going on in principle in an optical lattice. Things like motion in a trap, tunneling from one trap. I'm going to consider the simplest case of molecule as this. There's one molecule per side, and they're not moving in the trap. So they can rotate, but they cannot. And this is a good approximation if you have them in the ground state of let's say, of an optical tweezer. Yesterday, not trivial to achieve. But in principle, it could be achieved. And if your tweezer, let's say, is very tight, probably some of the motional degrees of freedom, or maybe all of them, can be neglected. So, but that is a good starting point for the derivation. So I'm going to do a quick derivation of the interactions between different rotational scans. So we have dipole interaction. So we have it's down 0, and up was 1, 0, and this is and additional projection for some external feedback. Can you see this? I'm sorry, better there. Change the angle here. Yeah, away from the right. Yeah, so this is our qubit setup, right? One qubit, there's a second qubit, right? So we're going to consider the interaction of qubits. Each of them is going to be like a qubit that affects spin-on toxic. So that we know that the dipolar interaction here is We wrote the same so many times that I'm almost reluctant, right? We have q equal to 0 component, which minus 3 cosine squared theta over r I j q times T0, the zero tensor component of dipoles on the mode plus 1/2, T plus D1, T minus 1, plus equation conjugate on that. So that's the dipole contraction, the q equal to 0 component. And the reason we're using q equal to 0 component is because we have m sub n equal to 0. So any coupling between the two qubits are going to be mediated by q equal to 0. So, and all you have to do actually to derive the interaction between the two qubits is to write down the matrix of this Hamiltonian order in the basis of two qubits, right? And you have one qubit basis can be zero up and down, right? That's the options we have for a single. But for two qubits, we have four options: up, down, 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 up, down, down. So the two qubit basis would look like we have four basis functions. We have up, that's the basis, right? So yeah, up, down, down, up, and down, down. So that's all that exists. Right? So again, what is the approximation here? We're neglecting the rest of the input space. And that is this projecting out. Yeah, basically, say all our Hamiltonian sits in this like acting in the subspace, which is of course neglecting leakage effects. So we neglect the effect of coupling of this space to the outside of the rest of the input space of the molecule, which is enormous. But we're going to ignore that because we're deriving this model from the physicists. So and this is very beautiful because now all we have to do is to calculate the matrix element. So, well, we know everything about that dipole, and we know everything about the matrix elements of the dipole in that electric dipole in the basis of rotational states, which are now our effective spin on half. So we can just take products, and this term will not survive because again it raises the lowers m sub n by 1, and then we have only 0 in the subspace, right? So doesn't happen here for this particular basis. However, if we choose, let's say 0, 0, and 1, 1, 1 minus 1, then this term will be important. They will actually change the sign of the matrix. So actually it will be different. But for now, let's just keep those two, and then we just calculate up, dipole. So with this term being the key term, the up matrix element is clearer because up is 1, 0, right? So just like 1, 0, dipole. The first of the mole. By the way, the first means like the first mole. The second means the second. Right? So this is D0, 1, 0, right? 1, 0, D0, 1, 0. Right? So up is a square of some number, essentially. So which is the expectation value of the dipole in that 1, 0 state, which we know is 0, 0, but we're going to write it up and write it down anyway. So we're going to call it D up. And of course it's squared, right? Because this is the same. Okay, does it make sense? We're going too fast, too slow, optimal. Right. So we can just go and do the rest, right? And just to illustrate, so let's say we want to do up, right? Up, let's say, okay. We want to do up, down, H dipolar. I'm not going to do all of the 16 images on it because it's too much work for now, but you can do it like in 15 minutes probably. You sit down and you write really, really fast. So it's kind of 1, 0, D0. You see what I'm just taking the product of individual images here. Products factorized because there's two diagonals there. This will move to 1, this will move to 2. So 1, 0, 1, 0 times 0, 0, right? The second is down. The second is down. So it's 0, 0. 0, 0, we're taking the matrix elements of D0 with 0, 0 here. And that is D up, right? Times D down. Exactly. And of course, no one corrected me, but there is a factor here, which I'm going to write proportional here. proportional, you can always multiply by this factor, right? You know the calculation. This factor depends on what you optimize. You optimize the square, this is just nearest neighbor interaction. So this is 500 nanometers. Some of the best optimized you know, they're very much closer than 500. And theta is the angle, remember, between the interdipole molecule molecule distance and the vectors between the dipoles, which we're gonna say that molecules are trapped in the tricky place. So this is zero. So we get just one more. This is just the three factors. But what is most important is the dependence on the expectation values and their products. But like another very important matrix element is actually up down the dipolar, down up, right? Up down down up. This is, and again we saw that before, it's something called spin exchange interaction of flip flop. So let's calculate. So this is, let's convince ourselves that this is actually not zero. So it's up down also, right? So it's 1 0 0 0 0 and down up on the other one. So it's going to be 0 0 0 1 0. This is d up down square because these guys are equal. Commission so equal to this, and this is equal to what they are not. Right? Okay, we can go, but these are the most important things to keep in mind. So if we do that for the rest of the matrix, like we can do it, and using this kind of approach, and once you get there, you get this matrix, right? So it looks like this.
Maybe so the first equation was the dipole dipole interaction was q is 0, and then you write it into 0 to 0 to. Those are only care about the components.
Exactly. Yeah, because there's no partial waves. Okay, don't know what I asked about partial waves.
So this kind of more about
Oh, these are components of that of each one. This is molecule 1, this is molecule 2.
Yeah, I understand. But the 0 0 and the 1 minus 1.
They are rotational degrees of freedom, and 0 is the point of that projection. So the projection of a momentum is so it could be arbitrary. But maybe John has some better answers. The matrix element of the dipole out there, we enable 0 and equal 0, that would be 0. Well, not if you have an external electric field. Oh, well, this is that's right. Yeah, because we will apply an external electric field. Just in a second. I didn't hear that. Yeah. There, yes, in principle, you're right. I mean, no field, this is the guy 0, but I'm still generating. Yeah, in principle, I mean, I think you talked about it, Joe talked about it, so I felt that,
Yeah, but everyone notation is the problem.
And in fact, if you had probably June here, he would tell that I have another mistake in my notation, which I do have, right? And in fact, I should be in an electric field. These are not good quantum numbers, right? So I should be using tildes over them, and I will be using tildes. Okay, so because an electric field, remember, 0 is coupled to 1. Here you talked about it. So 0 is not really 0, so that's why I'm going to put a little bit. Okay, so but this is just notational.
Well, but like, what is the difference between D0 and D1?
Oh, the 0 and the 1 is this guy and this one.
Yeah.
These are just this is 0.
This is the spherical one.
Yeah, it's y1 is equal to sine theta, and this is like sine theta. There's no difference. But this is just, I think John, like derived this carefully. And I mean, I'm not gonna repeat this again. So, and in fact, another point that this question brings is that there's no partial waves. You remember, John talked about partial waves and dipole interaction coupling different. There's no L. There was another spherical harmonic here, which I'm kind of like putting under the rug. And the reason is that we're considering molecular optical or an optical eyes. There's no relative motion. And we're considering them P. So therefore, there's no need to trade. This is one of the great things about optical lattices, is as opposed to collisions, you don't have to worry about function. Oh, not quite. Until we start considering them. Eventually, for this simple models, no partial. Okay. So we can get this, right? So I hope everyone now is on the same page with regard to this matrix, and you believe me that this matrix is there, right? So this is a very important matrix. So make sure if you have any questions, maybe ask. So that we're going to proceed, and we're going to just do some tricks as usual. So now, what's the point of all of this exercise, really, ultimately? We want to rewrite it in terms of effective spin-on-half operators, right? Because in condensed matter physics, this complexity is best to have a very compact and as small and simple as possible representation of interactions, which we already projected on spin-on-half ways. Now let's derive these effective spin operators on each molecule, right? Because we have effective two-model system, we can have this, amazing apparatus now of spin-on-half, right? Of quantum mechanics, spin algebra to serve us. We can now engage the apparatus, the formalism, and say, okay, up minus down is my S sub 0, right? And my up and down is my jump operator, like in normal quantum 1 or quantum 2. So these jump operators, they flip spins, right? S plus and S minus, they're just conjugates of each other. These guys are not Hermitian, but S sub Z is I should say sub Z now, because we have both molecule index and the projection index, which index comes at the top of the spin, right? Usually it's used in the bottom, but because we have I somewhere else. So if we do that, and you write something like this, which is like J perp over 2 Si plus Sj minus plus Hermitian conjugate plus J sub Z, S sub Iz, S sub Jz, which is Ising interaction here and spin exchange interaction. You can actually show that if you calculate matrix elements in the spin in this basis for up, down, down, up, and up, down, up, you get exactly the same matrix as we were talking about here. You get exactly the same matrix like this, but with the coefficients J perp and Jz expressed in terms of EDM matrix elements on the molecule, right? So you're doing here, what you're doing here again. It seems like unnecessarily complicated, but what you do, you want to describe since you have effective spin-on-half, you want to describe everything in terms of spin operators, right? Spin-on-half. And if you introduce this operator, you'll show that its matrix elements in our 4 element basis is exactly the same as our 4x4 matrix if we identify this constant properly. So the question is, what should this constant be, right? And for that, you have to compare essentially. And I'm going to again do a quick run here, quick calculation. So, and I want to keep on the slides this matrix here. So let's say we want this matrix, the matrix of the spin operator, has to look exactly like this, right? We're trying to fit in other words the parameters in operator products into this dipole model. So and okay, so I'm not going to derive, so this is kind of a little bit lengthy computation, but some of its elements can be understood quite easily. So what you do essentially, so you basically write down, your J perp over 2, for example. Let's focus on the screen, spin exchange term, right? The spin exchange term is here. And our basis set is, again, up, I just erased it, unfortunately. So I have to write it all again. Down, up, and up. So we have to calculate this operator acting with these functions, right? Evaluate its matrix and then compare to that. And miraculously, it will be very similar. You just have to read all their coefficients. And then I'm going to prove is like J perp is equal to T up down squared. But it's a very easy proof. So let's calculate Si plus as J minus just in this basis, right? So we have to act by again onto 1. What is that? This acts on this guy, right? This acts on this guy. First on first and second on second. This is just two molecules. Yes. S plus is raising already spin polarized state. I try to raise all this spin polarized, which is like 0. So, okay, Si plus Sj minus acting on The next guy is up, down. 0 again, right? Because the first guy is actually already spin up state. You cannot raise it above. The qubit space ends there. So 0. Then you get, maybe you get some luck on the next one. Down, up. Now here, not 0 anymore, right? Because this raises this guy and this guy lowers this. So this is 1. Right, and then Si plus Sj minus and down, down, again 0. So this whole matrix, this operator, the 4×4, only has one non-zero element, and but when you can conjugate that partner, it has 2. And so the matrix, let's write it down. It's not a hard matrix to write down. Well, let's this be our basis, and then another up, 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 down, down, up, down, down. Here, 0, 0, 0, big fat zeros everywhere pretty much, excluding up, up, down, up. 0 here, not 1 here, 0, 0, 1 as the evolution, right? Right? So you see that d squared over up down squared, right? So that has to be our prefactor, right? In order for everything to match up, right? So we have just proven by comparing this matrix to the dipole-dipole interaction matrix, which is derived, that this constant J perp is actually equal 1 minus 3 cosine squared theta over R by J T up down squared. So this spin, which makes sense because we know that the point-flop interaction actually is caused by the diagonal transition dipole, right? So in a similar way, you can actually go and derive the rest of this matrix. If you want to play with it, it's actually quite fun. And in the end, you obtain these important relations that this so-called XXZ Heisenberg Hamiltonian or XXZ model with J perp equal twice, and I forgot the factor of 2. Oh, because it was divided by 2, sorry. Put the factor of 2 there. Yes, we divided by 2. So twice d up down squared, and the Ising constant is actually d up minus d down squared. This is actually a little bit harder to derive, so that's why the lecture, it may take like half an hour, but it's still, if you're interested in this stuff, you should convince yourself that this is the case. So these guys, these additional terms, W, V, stuff that comes into this kind of terms, they actually, if you consider pin molecules, at unit length, and not tunneling, but pins, so these terms do not matter. So these terms start to matter when you allow molecules to tunnel, and this is the so-called TJ model, and Anna Maria Ray and Alexei Marshall, they had a great paper about it with Drew, which I kind of recommend, which I think Simon was referring to in this talk. So it's a very long PRA paper, but it's amazing, unlike most PRA papers. So we have derived the effective dipole-dipole interaction between 2 qubits, right? This is spin flip-flop. And what is this? We haven't talked about this that much yet. And John didn't talk. He didn't talk about it really. Because it's a zero electric field, right? Because d up, remember d up is equal to d down at 0 electric field. So if you don't have external electric field, all you're left with is this term, right? And then, but I'm actually, because this term has been explored to death. There's been a lot of papers and a lot of studies. So I'm going to instead focus on this term. So actually, this term is a constant of the function of it. It doesn't change much with electric field. That's small. It goes down. So, but this is the Ising term. What is interesting about this Ising term, like 0 at 0 electric field, actually goes up with increasing electric field. Why is that? Because the dipoles in, if you are to plot the expectation value of the dipole in this state, it will go down like this, and here it will go like this, right? And basically, the difference between them is going to give you this Ising complement. And how do we understand this? Well, you see this interaction SIC/SJC here. It means that when the spins are pointing up and down, the interaction is exactly the same. But the spin, when the spin is pointing up and down, the energy of this is different from the interaction of them pointing both up. Right? So up is different from up down. And because up is different from up down, this is the essence of this Ising interaction. And this is what you can use to actually generate entanglement if you only have pure Ising interaction, as I'll show you in some next slide. So the energy of up, remember, is different from the energy of up down. It's not as spectacular as Ising interaction, which is like going somewhere and very beautiful to understand. Ising interaction is not so almost kind of boring, but it's actually very useful, as I'll try to convince you why. So okay, so this is what Kankman's. Sure. Yeah.
The energy differences are very small, right? Doesn't this make them very fragile towards anything?
Yeah, of course.
Do you know these are maybe something or?
I believe so. The time will show, and as experiment. I mean, remember those DiVincenzo criteria, right? You'll have to
1,000 of the vibrational level, only 1,000 of the electron text.
You mean, are you asking about the split? The energy scale is like like fraction of therapy. So to see some of this coherent, but remember, there's a lot of so actually June in 2017, they observed coherent oscillations due to this fluid electron in optical lattice, and they didn't have unit field. So they had randomness, like gas with a fairly modest entropy. So not every unit is in the lattice setup speed. And even in that setup, the interaction is and it was 10 years ago. Now it's things that. Yeah. So so we're not going to talk about these terms. Read Alexei Boshkov's paper, Anna Maria Ray's paper on interesting implications of this. And TJ model is very interesting as well. If you allow molecules to tunnel, it actually mimics the things like high TC superconductors and stuff like that. So you can engineer all of that, state-dependent tunneling and stuff like that. So very beautiful stuff. But for gates, let's say if Kankman talked about this as being very promising for engineering spin exchange interactions in zero electric field, right? So what you can do is actually I think I really like this paper because it's the idea can be actually understood just in a single figure. So you just basically excite qubits into different rotational states, and then you wait for a certain phase until you build up enough phase for the interaction kind of not fully jump, but maybe like half jump before the coherent superposition, if I understand it correctly, of the plant of two molecules. And that is actually I-swap gate, which is similar to kind of or swap gate, but it's a universal quantum gate. So with that, you actually can build a quantum. So you don't, all the rest you need just single molecule gates, which can become a macro. So this looks great, but rotational states have limitations. Okay, so some of the limitations are that, first of all, the pole interactions are always kind of warm. So it's really hard to pull them out. Right? Because if you have zero electric field, the moment you put in molecules in this rotational states, like in this qubit state, they start to interact with each other. And maybe it would be nice to be able to sometimes switch them on, or provide these interactions on demand. Then coherence time is short, they're improving. This is not a fundamental limitations, and quantum control requires strong DC electric fields. Again, this is not a fundamental issue, but molecules have so many states. Can't we just maybe use some nuclear speed or electron speed states to mitigate some of those limitations and maybe generate interesting states in the end? And of course, the answer is people looked into that already. This is a figure from Simon's paper on n equal to 0 nuclear speed levels. And we see that there's quite a bit of states, and they're all n equal to 0. And because they're all n equal to 0, there's no interaction. Right? So because remember, JZ is proportional to difference between dipoles, and all these EDM matrix is 0. And because of that, That's it. So the molecules are not talking to each other, and because of that, the coherence times can be very long, in excess of 4 seconds, and demonstrated in groups, at least as far as in the 3 groups already, independently, but maybe more. But this is the problem with nuclear spins. If you encode it in a different, remember, this is encoding, different encoding. You stay in the ground rotational states, but you use different nuclear spin states. This is useful for quantum information storage. So you can just, put this population of coherence there and wait, and it will not fade, or it's very useful. But can we make them? The problem is that you cannot make them interact. So nuclear spins notoriously difficult. They just don't want to talk to each other. The interaction is so weak. And so, can we make them talk to each other? And the answer is actually yes. And we have shown that if you choose the qubit in a little bit more crazy way than people choose before, such as you choose the ground rotational state with certain nuclear spin projection, and then excited rotational state with a different nuclear spin projection, right? In this case, 0, 0, M, 0, 1, 0, M prime. Very different from this because nuclear spins are now different. And because of that, what can you gain? What can you gain? Well, this is the diagonal elements of the dipole moments in this new encoding. Different, we call it spin rotational encoding. In this spin rotational encoding, the diagonal matrix elements are exactly the same as in the rotational, because these are different nuclear spin states, right? However, the off-diagonal elements are 0 all the time, right? Because there's nuclear spin symmetry, and nuclear spin, the EDM doesn't know what nuclear spin is. It's completely diagonal to the nuclear spin basis, with M not equal to M prime. So they have different nuclear spin symmetries, and therefore 0, identical. So there's no flip-flops. It's the anti-dipolar spin exchange conjugate. Or there's a name for it, actually, I figured out this NMR. It's called, you can engineer Eisenberg. Yes.
Sorry, can you clarify the location here? 0, 0, M, what do they represent?
0, 0, M is the ground rotational, this qubit.
Yeah, what is 0 here?
0, 0 means like the same 0, 0 is here. Ground rotational state, ground and 0 projection of rotational angular momentum on the magnetic field axis.
And the
M represent both nuclear spins of K and RB. So there's like 36 possible combinations of these guys for the kind of KRB molecule that Gila and Composite experiments look at. So the M is like nuclear spin collective, nuclear spin. Yeah. Okay. So you see here, see how many, right? So these gray lines, actually, they're real molecular states. Just we just picked one, but you can in principle pick another one as well. So, but this is very different. This is the opposite of the flip-flop business that we talked about. So only Ising interaction survives here. And this is, again, we are back to, see, this is just to illustrate, because now this guy is 0, but these are not 0. So you get the Ising model with long-range interactions. And the nice thing about Ising model is that it's very well understood. That's not the physics community, because everything commutes, right? These operators commute on different sites, unlike the XZ model. You can actually write down the solution even for time dynamics and yes.
Well, as an experimentalist, I made the point that if you turn on the electric field, then the starship is very large.
Yeah.
Therefore, you have to control it really well compared to the interaction. So what kind of interaction are you, what's strength of interaction?
Yeah. So here you would use electric field for KRB for at least a few kilowatts until that appreciable Ising.
Sure, but I'm just saying, in terms of comparing actually the strength. Okay, you say 0.02 kilo.
It's in for example, it's this plot, right? It's the same as in.
Right, and then but this is on top of megahertz or gigahertz shift.
That is true.
Single particle shift.
Yeah.
Right. So
and that is a disadvantage. I agree with that. But
a huge disadvantage.
It is. It could be. Yes. All right. Okay. Hopefully, it's not a killing disadvantage, but I appreciate the fact that it's a problem. It can be experimental, but I'm a theorist, so I just write down the interactions and see where it can lead us. Maybe someone will invent a way to control it so much better in the future that it will be useful, right? But I agree. I mean, electric fields is a complication, right? And you don't necessarily want to work as an experimentalist with large electric fields. So, but anyway, so before I think this I'll show you in a second that in a few slides that these interactions actually give rise to very interesting many-body entangled states that are called cluster states, and which are a very important way of, or the way of doing. You can actually just do quantum computing based on single measurements of these cluster states. You don't need anything else. So-called one-way computing.
How do you ensure you consider this two state, like
Mhm.
the 0, 0 same kind of state?
Mhm.
They're
Yeah.
how do you ensure they're not accurate?
You mean?
But considering 1, 0 and 0, 0 and 5,
Yeah.
like 0, 0 and it also enters component.
Yeah, sure, but you can put the population of the molecule in the state. All of that. There are coherent control techniques. You can create molecule in the control. Yeah.
States, but then
Well, no. Well, if you are careful and you can create coherent superposition with high fidelity, and it will not be all states. You just because actually June Yee's group at GWA have demonstrated already 13 years ago, very high level single molecule control. And there's a paper on physics about that. It has been improved. So, but this superposition is not trivial to create because you cannot just pulse with microwave this guy, right? Because it's M is not equal to M prime. So you have to use an intermediate state, but it can be done. So anyway, so I just want to offer you like straight out there.
But I mean, the same mapping could be like 0, 0 to 1, 1, right?
0, 0
Like
to
you're up and down, it's 0, 7, 1, 1, and
0, 0, 1, 1. 0, 0, 1, 1 will be a different mapping because it will have X term. It will not have. Here, I'm trying to kill the X portion and have pure isotope.
no, you would, it's just the mapping.
Oh, you mean like 1, 1 with a different speaker?
Yeah, position of 1, 1.
Oh, sure. Yeah. That is true. Yeah. It obviously not limited to 1, 0. Yeah, you can choose 1, 1 as well. That is a good point, and that will change the sign of your J perp and everything. So it's good. But I just want to emphasize that there's so many, as you see from this plot, there's so many rotational states or nuclear spaces. It's kind of like confusing. What states are reasonable as qubits and what states? What can you even expect? And actually, we have thought about it, and we have, and in collaboration with Roman Krems and his student Kasra, we thought about a way of generally classifying molecular qubits based on the electric dipole interactions. Actually, if you think about how these qubits interact, you know there's only XXZ and X interaction, right? The flip-flop and the Ising term. And so there's only 4 possibilities. Even if you have 0 Z interaction or Ising interaction, or 1, or you have 0 or not X interaction, right? Based on that, you can actually define 4 classes of qubits. And let's say I call them like arbitrarily because I was sitting yesterday, preparing this slide, and I couldn't come up with a better notation as 0, 0, 0 qubit, 0, 1 qubit, 0, 1, 0, and 1, 1. So let's say 0, 1 qubit is the qubit that has no Ising interaction, but it has very strong X interaction. This is the conventional rotational qubit that we talked about. This is great because it can be realized at 0 electric field. Don't have to worry about nuclear spins, and good for things that involve spin exchange. Now you can imagine a situation where both of these interactions are active, right? 1-1 type field, where it's like would be a rotational state in general non-zero electric field, right? If that happens, you have both of these interactions, X and Z interactions, which can be advantageous for many things, like for example, quantum metrology, the generation of spin-sweep states. And I'll talk a little bit about that too. So now, if you switch off both interactions, like you get 0, 0, right? It doesn't interact at all. And then you're back to this nuclear spin sublevel case, where it's good for quantum information storage. So it's also good for something. That's amazing. So you can store quantum information until you need it later to pulse it into something, right? Finally, there's this crazy qubit that I just told you about, which no one has considered, which is 1-0 type qubit, where you only have Ising term, but you have 0 flip-flop. And I won't tell you, crazy, which I knew, but it's maybe useful for something, right? And I'm going to show you why, what can potentially be useful. But before, I'm even going to show you even crazier stuff. So Roman student Kasra and Roman Krems have been working on encoding. They were working for other purposes like quantum engineering. Because at UBC, super sure they have this D wave, and D wave is interested in things like qubits as well for other reasons. Using anneal stuff to anneal the unit too much. So they just pick everything and just study it for quantum engineering. But we started talking about crazy stuff, and then what about we thought if we put qubits at 0, 0 and 2, 0, right, with the same nuclear speed, right? It's not unheard of. You can nowadays, you can have different manipulation techniques like Simon can have this. You can populate many rotational states with high fidelity. So why not put them in 0, 0 and 2, 0? Okay. If you do that, you actually, and you put in an external electric field, you have alpha, beta, gamma states, which is like mixtures, like or a coherent superposition of different rotational states. Now, 0, 1, and 2, they all get coupled, right? They all get coupled in an electric field. So, and what you get is, like, this is like for so and so forth, it's very interesting. It actually turns out, I want you to look at this blue curve, and the blue curve shows the diagonal matrix element of alpha, alpha, which is 0, 0, which is kind of no surprise at all. We saw that many times, just the expectation value of 0, 0 goes up, but you see expectation value of 2, 0, which is beta, in this case, it's gamma, right? Gamma goes down. What is kind of interesting is what happens to the off diagonal between alpha and gamma, between 0 and 2. And this dipole action between alpha and gamma first shoots up a little bit, but then it actually settles back to 0. Which is like, you may be wondering, what's going on with this dipole between 0 and 2? Why is it even 0? And the fact is that there's second order coupling. You see this ground state alpha couples to 1, 0 and 1, 0 couples to 2, 0. So gamma couples to 0. So there's like second order coupling. Through that coupling, actually there's a maximum in the of diagonal EDM between 0 and 2 rotation. So I don't know what it can be useful for. So this is, for example, some example of this J-perp constant. Or in fact, see, Ising constant extremely happy. Ising constant is very large in this setup, again, as a function of electric field. But turns out that the J-perp constant, which is this blue line, is actually very square. Because why? Because it's a square of the diagonal dipole, and this dipole only exists in second order for this 0 and 2 rotational state. And because of that, if you increase the electric field actually quite a bit higher than this maximum, or you can barely see this maximum, but the scale is pretty large. So you see that it's almost, again, pure Ising model. So you get, but interestingly, the qubit goes from 0, 0, 0 electric field, there's no interaction. So this is a multiple type qubit. So at 0, 0, at 0 electric field, you can use it for storage because they don't have only time. Right? But if you crank up electric fields, goes to 1, 1, quickly switches over to 1, 0. Which means like there's a qubit type crossover in this classification that you can experience by just changing the electric field. So you never need to actually remove the population from those states in order to control the dipole interaction. So you get maybe the best of two worlds. You get no interaction with 0 electric field. You start to increase it, you get them to interact essentially. So this is a new type of qubit, which I hope someone someday will realize. But this classification that I showed you should be general enough so that any person who is thinking about realizing new qubits could figure out what they can be potentially useful for generally. Right? Okay. Any questions before I move on? And how much do you Okay. I have to go quickly now. Now, interesting stuff. Entangled state of molecules. All right, so this is a very recent topic that people started to work on. It's the RESTful community. Again, it was initiated like so many things by Gila. Gila is leading the world in this, and Anna Maria Ray in particular, and now Thomas Milutevsky is a student, postdoctoral student at Gila. So the good thing about these qubits is like once you figure out the interactions, right? It's not just you can do like quantum computing is only one of the possible things that you can do. The other thing you can do, you can think about quantum metrology, for example, generating many-body entangled states using the interactions that you have derived. So the interactions that you derive are useful in many ways. So that's why it's so interesting to derive them and so profitable. So for example, and again, I talked about it, entangled states cannot be factorized. And as we know, into products of two states, of bipartite system in this case, psi1 times psi2, and Bell states. So can we engineer these entangled states with ultra-cold molecules and optical lattices? And the answer is yes. So first of all, let's talk about Ising interactions. And for Ising interactions, it's well known that the kind of states you get is the so-called cluster states. The dynamical evolution under the Ising Hamiltonian can be actually analytically calculated, which is amazing in condensivity in the world. It's probably the only thing that can be calculated analytically because everything can be through that. And what you get, like for 2 qubits, is you get so-called Bell state. And again, we talked about it yesterday. So what you do is basically you have 2 qubits, you let them interact, and then you stop the interaction after a very, very well-defined time. So they pick up the phase, and remember the phase of this is different the phase from this. So these states get a relative phase between them due to the Ising interaction. That creates entanglement. And you may be wondering what is LU. LU is so-called, is local as LOCC equivalent. It means like no matter what. So basically, it's not sensitive to the single qubit rotation. So you can rotate each qubit, and it will still be equivalent because entanglement is not sensitive to unitary transformations on single systems. So you can rotate these guys as and the entanglement is not very cheap. So that's what LU means. So anyway, for 3 qubits, you can get GHZ state, which is useful. But for for 4 qubits, it's not a GHZ. And so these guys, Briegel and Rossendorf, they investigated the states extensively in this paper, and they show that these states actually have localized entanglement, and they're great for things like quantum one-way quantum field. So you can do all quantum gates by just preparing this single huge cluster state and then measuring it different in a very, very well-defined way. You cannot just measure it however you want. You have to measure it way. But then actually it becomes equivalent to gate-based one. And this paradigm is it's pretty old. It's not as old as gate-based one. It's getting significantly less attention, probably than it deserves, given its universal character. But I think there are at least 3 or 4 groups still that are working in atoms trying to realize these states. And it has actually been done. We realized it multiple times. But the challenge is they are trying to realize 3D cluster set. Actually, the beauty of this cluster set, they're actually relatively robust 3D coherence, single particle coherence, as opposed to GHZ state, for example, which like you decohere 1 qubit and everything just falls apart. So this guy, if you decohere 1 qubit, your things do not fall apart for you. So you can still carry on essentially quantum computation with less perfect. You can still survive. And in 3 dimensions, actually, it becomes even better. It becomes even better in 3 dimensions. So pretty much this is the protocol we figured out in this paper with Anna Maria and June on creating this cluster states with alpha diamonds and optical lattice. Pretty much, you fill the optical lattice with molecules, right? Easier said than done, of course. Then you basically create the superposition of initial states of different m's, and remember m that has to be different from m prime. But now we realize that we can also do the same protocol with 0 and 2 states. So we can do exactly the same thing with anything that interacts via Ising interaction. So 0 and 2. At that time, we didn't know that 0 and 2 is so interesting. So, but this is general, and then you start the superposition, you start evolution, right? The moment you excite the superposition of different m and m prime states in different rotational states, actually start to be coupled by the Ising Hamiltonian, and they start to evolve into this cluster state. And then you wait for pi over jz is the Ising constant, and then you stop your evolution by transferring the molecules back to their rotational ground state. And the reason we are transferring them to rotational ground state is because this has very long coherence time in rotational ground state. And in the end, you end up with this cluster state of ground state molecules that is sitting there forever. And you can have the luxury of, okay, I'm going to measure here, there, and maybe implement some of this, intricate protocols of one-way quantum. So that's kind of like the idea. And I know this requires electric fields, that's for sure. But let's maybe switch gears a little bit and talk about quantum metrology. So cluster states is not the only interesting entangled states, the state that we can realize. We can realize things like, for example, quantum spin squeeze states. And I don't know how many of you are familiar with that, probably many of you are, but just to give you a gentle introduction. So this is this great paper that I highly recommend by Toss and Appalanas in JFIS A. is like amazingly, simple explanations of most of quantum metrology concepts. The best I ever seen. So I use it in my quantum distribution class. The student one. So basically, I stole it from there. So you think about metrology, right? So you're basically trying to measure, let's say, magnetic field with n unentangled spins polarized in this direction, right? So this direction is actually pointing towards me, and this is y direction. So, and like you couple them to this large collective spin, and the spin precesses around the magnetic field, right? As we know. And basically what you measure the phase of that precession, right? You measure the angle, theta, and you're trying to maximize the resolution of that measurement. You're trying to become very good at measuring this angle. And basically this is like a clock. So this collective spin, like this red line is the red arrow, is like not just a single molecule, it's like S1 plus, S2 plus, it's like a huge spin, like macroscopic spin, you have a large number of molecules. And it precesses, and this is like a regular spin, coherent spin state, right? So it also precesses due to quantum mechanics around this J sub z, around this one mean value. So it precesses around magnetic field, and at the same time it precesses around the mean value, right? And the phase resolution that you can gain on that magnetometry measurement actually determined by how much it precesses in the direction perpendicular to the mean value, right? Because if it precesses like this, these guys overlap, this Heisenberg circle overlap, and you cannot measure the phase clearly, right? Better than the overlap between the Heisenberg circles. Yeah. Does it make sense, right? So what do you do? Like for coherent spin state, are you hopeless pretty much here? So this is a limit that's called standard quantum limit due to this. You can actually pretty easily derive it as a, because expectation for coherent spin state, the expectation value in the perpendicular direction of the delta Jx is square root of n. Square goes like n. So the precision of phase is just like this divided by the magnitude of the direction, just like cosine moment they were in high school trigonometry. So it's like when you plug in the numbers, you get 1, right? What do you do if you want to do better than this? you squeeze the uncertainty, right? So imagine like one way to improve it, right, would be to squeeze it along this x-axis. If you squeeze it, obviously, you can better measure the phase because the uncertainty in the perpendicular direction is now, in the x direction is now, so the overlap is reduced. So what you do is basically, right, pretty much decrease delta Jx. From this plot, it's very clear how this quantum metrology works, right? This was spin squeeze states. So and then now you just have to look at the Heisenberg uncertainty relation, right? And so delta Jx, delta Jy, you cannot squeeze and still get the same uncertainty on the y direction. You squeeze in the x direction, and your uncertainty in the y direction shoots up. But their product is greater than Jz, and this is kind of constant because you know your number of spins in the system, right? It's determined by the total number of particles. And so you can decrease delta Jx, but then of course Jy it increases, but you don't care because it's in the direction that you don't care about for measuring this magnetic field. It's not the direction of precession, right? So this is kind of the maybe 5-minute introduction into quantum metrology and spin squeezing, but I hope you got the main point. So if you reduce the uncertainty along the x direction, below the mean, the square root of the mean value of spin along the z-axis. This is called spin squeeze state, and there are important papers in the field by Osmomer and Monica Schler-Smith, and they show that this is actually equivalent to the presence of many body entangled. I'm not going to prove this, but if you require this, you must require mathematically that the states can no longer be independent. There's an important paper, like we can talk more about that. It's in this review, so. But again, the most quiz. So, but the ideal limit you want is you want to beat completely the standard quantum limit and go to a limit where the phase resolution is precision is proportional to 1 over n, as opposed to 1 over square root of n, as with normal standard quantum limit. And if you do that, that's obviously the holy grail for a lot of people, right? Because you can measure something so much better with a small amount of number of quantum entangled particles. You can measure as much ideally with 100 entangled particles than with 10,000 unentangled particles, and then you can do the math on that. And obviously, this is, perhaps the greatest challenge and the greatest reward in the field at the moment. But pretty much this can be done, as Anna Maria Ray and Jun Yi and Thomas showed in their latest paper, with molecules in rotational encoding of the qubits. So you get this model you're probably already tired of. the XXZ model. And they showed that you can actually engineer, this model gives rise to dynamical generation of spin squeezing in model. Right, so I was very intrigued by this paper. So when I went to GILA, we actually generalized this to, this is obviously sensitive to the splitting between the rotational ground and rotational side state. So this is kind of electrometer, if you will. So you can measure electric field very well, and anything that depends on splitting between the ground and rotational side states. But actually, in this paper, we generalized this argument to magnetometry. So if you're interested, this is packed with results, probably so easy paper to read. But it has some beautiful pictures, so I invite you to go and read it. And pretty much you see outer cold molecules can actually be used to measure things beyond the standard quantum limit, as this new research suggests. So I just want to thank, my great collaborators at GILA, June and Anna Maria, and at UBC, my former advisor, Romo Krems, and his great student, Kasra, for doing this research with me. And I'd like to thank you all for your attention.
Kind of in terms of experimental implementation of like a icing type Hamiltonian few slides back. Just what is like the scale that you need to decrease the non-icing interaction to before that you like? So for me, that would almost show as like ecoherence system, like you're ruining the state that you're creating via interaction.
Yeah, it's a very good question. So typical evolution times, we have in this paper calculated the evolution time for, and I was showing the protocol, right? You're asking about the protocol.
Yeah, just how good you have to get that other.
So this evolution time has to be much smaller than the evolution time under other parasitic or like extraneous undesirable genes, such as X and Z in this case. So typically for KRB, this is about 16 milliseconds at 500 nanometers. So you would want to suppress this to way below 1 order of magnitude. However, we have actually estimated in this paper the effect of noise on the cluster states, and there are mechanisms to help you. For example, Anna Maria has this great paper with Michel back in 2008 on so-called gap protection. So you have a many-body gap in the spectrum of this quantum many-body system, which you have for certain relationship between JZ and JX. Actually, it actually helps you fight incoherence. So, and also you can use spin echo techniques to extend this coherence times, right? Again, I haven't described them in detail, but pretty much you want this to be like much shorter than any undesirable coherence time. So you want other constants to be much smaller, at least by order of magnitude, I would say, but the more the better. Well, I'm still here for the rest of the day.
That's a good question, but I wonder how the direction, how to turn it on or off.
You cannot if you have this the spin if you have this flip-flop, if you stay in the same state in the space, you cannot turn it on. And that was one of the motivations. I mean,
but the scheme that I have there, it has.
Yes, but you have to pass in the critical state. Yeah, that's
That's how you switch on.
yeah, and yes, and this is what I was about to say. In if you don't want to deal with it, or you just keep the information in nuclear spin state, and then you apply, let's say, bypass to go to another state where it's actually active, the coupled by dipole interaction. So this is also a great way to switch on things. Again, like I'm not saying that, but for this kind of qubits, you can switch on by just tuning for this crazy qubits 0-1 type. You can just increase electric field. And then it will the interaction will switch on. You don't have to worry about transferring the amount. But then you have to worry about electric field. There's always like yeah, maybe transferring is easy. I don't know from external viewpoint, it's probably easier. Yeah, okay. All right. All right, well, okay.
Shall I leave this here?
Okay.
Well, let's make him, for him.
I hope it was clear.
Leave it to two, I have to think about it. You can have so many other things. I mean, you can spend like the entire. Third order.
Yes.
So you. I'm on your, so what I wanted to ask is, I do, yeah. Maybe surprise somebody else. Put it on, no, put it on the main. Okay, is that the Windows? Yeah, yeah. Let me try that.
Someone sitting here? I'm gonna sit here. Yeah, this is unoccupied. Thank you so much. Yeah, nobody ever saw that. This is why this chapter. I remember I was starting this. And right, this is. It's amazing.
Yeah, sorry, I'm just wondering, can I see your last slide? Because you showed a nice tape and I missed it. I just wanna.
Do you just leave? It's in an archive. I mean, it's like you mean the reference to this?
No, that before.
Oh, the
this-
metrology paper? Or
Yeah,
the-
yes, this one. I just wanna
June's paper, like 2021 field is aware.
take a picture. Thank you very much.